The U.S. Chemical Safety Board is developing a new interactive training application focused on OSHA's Process Safety Management, or PSM, regulation. The training will cover the 14 elements of PSM using the 2005 explosion at BP's Texas City refinery as a model. Look for it soon at csb.gov. March 23, 2005, the BP refinery in Texas City, Texas. Several units at the refinery had been shut down for lengthy maintenance projects, which required nearly 1,000 contractors to be on site, along with BP employees. BP had positioned a number of portable trailers close to process units for the use of contractors and other maintenance workers. Over a period of months, BP had located 10 trailers for workers servicing the Ultra Cracker unit, including a double-wide wood-frame trailer that contained 11 offices and was regularly used for meetings. Though these trailers were located near the isomerization unit, the occupants were not warned the ISOM unit was about to start up, a potentially hazardous operation. At 2:15 a.m. on March 23rd, overnight operators began introducing flammable liquid hydrocarbons, known as raffinate, into a 170-foot tall raffinate splitter tower used to distill and separate gasoline components. Near the base of the tower, there was a single instrument that measured how much liquid was inside. It transmitted this information to both a satellite control room and a central control room located away from the ISOM unit. But this level indicator was not designed to measure liquid above the 9-foot mark. During normal operation, the tower was only supposed to contain about 6½ feet of liquid. But during startups, operators routinely deviated from written procedures and filled the tower above the 9-foot mark, concerned that if the liquid level fluctuated too low, it would cause costly damage to the furnace. At 3:09 a.m., as the liquid neared the 8-foot mark, a high-level alarm activated and sounded in the control rooms. But a second high-level alarm, slightly further up the tower, failed to go off. By 3:30 a.m., the level indicator showed that liquid had filled the bottom 9 feet of the tower and the feed was stopped. The CSB later estimated that the liquid was in fact at a height of 13 feet, but operators could not know the actual level because the indicator only measured up to 9 feet. The lead operator had been overseeing the startup from a satellite control room within the ISOM unit. At 5 a.m., he briefly updated the night board operator in the central control room about the startup activities. The lead operator then left the refinery early, an hour before the end of the shift. A new board operator arrived in the control room around 6 a.m. to start his 30th day in a row working a 12-hour shift. He spoke briefly with the departing night shift operator and then read the logbook to prepare for the startup. But the logbook did not clearly indicate how much liquid was already in the tower and equipment, and it left no instructions on routing of the liquid feed and products when the startup resumed. Instead, the control board operator only found a one-line logbook entry that said ISOM brought in some RAF to unit to pack RAF with. At 7:15 a.m., the day shift supervisor arrived. Because he was more than an hour late, he received no formal briefing from personnel on the night shift about conditions in the ISOM unit. At 9:51 a.m., operators resumed the startup. They began recirculating the liquid feed and adding more liquid to the already overfilled tower. As new feed was added, startup procedures called for regulating the liquid level in the tower using the automatic level control valve. But the board operator and others had received conflicting instructions on routing the product. As a result, this critical valve was left closed for several hours, blocking the flow of liquid from the tower. A few minutes later, operators lit burners on the furnace to begin heating up the feed. part of the normal startup process. While the startup was underway, the day supervisor left the refinery on short notice, just before 11 a.m., to attend to a family medical emergency. Contrary to BP's own procedures, no experienced supervisor was assigned to replace him. This left a single control board operator, now without a qualified supervisor, to run 3 refinery units, including the ISOM unit, which needed close attention. The refinery had eliminated a second board operator position following corporate budget cuts in 1999 after BP acquired Amoco. As the startup continued, the tower steadily filled with liquid, reaching a height of 98 feet shortly before noon, more than 15 times the normal level. But the improperly calibrated level indicator told operators in the control room that the liquid was at 8.4 feet and gradually falling. Furthermore, the control panel was not configured to clearly warn operators of the growing danger. It did not display flows into and out of the tower on the same screen, nor did it calculate the total liquid in the tower. Meanwhile, the maintenance contractors, who were not involved in the operation of the ISOM unit, left their work trailers to attend a company lunch, celebrating a month without a lost time injury. At 12:41 p.m., an alarm activated as the rising liquid compressed the gases remaining in the top of the tower. Unable to understand the source of the high pressure, operators opened a manual chain valve to vent gases to the unit's emergency relief system, a 1950s-era blowdown drum that vented vapor directly into the atmosphere. Operators also turned off 2 burners in the furnace to lower the temperature inside the tower, believing this would reduce the pressure. Nobody knew the tower was dangerously full. The operators did become concerned about the lack of flow out of the tower and began opening the valve to send liquid from the bottom of the tower to storage tanks. But this liquid was very hot. As it flowed through the heat exchanger, it suddenly raised the temperature of the liquid entering high up the tower by 141 degrees Fahrenheit. It was now about 1 p.m. Contract workers, unaware of the startup and the looming danger, returned from lunch and began a meeting in the double-wide trailer, in the corner room closest to the blowdown drum. Over the next few minutes, the hot feed entering the tower caused the liquid inside to start to boil and swell. Liquid filled the tower completely and began spilling into the overhead vapor line, exerting great pressure on the emergency relief valves 150 feet below. At 1:14 p.m., the 3 emergency valves opened, sending nearly 52,000 gallons of flammable liquid to the blowdown drum at the other end of the ISOM unit. Liquid rose inside the blowdown drum and overflowed into a process sewer, setting off alarms in the control room. But the high-level alarm on the blowdown drum failed to go off. None of the operators knew of the catastrophe unfolding in the ISOM unit. As flammable hydrocarbons overfilled the blowdown drum, operators nearby saw a geyser of liquid and vapor erupt from the top of the stack. The equivalent of nearly a tanker truck full of hot gasoline fell to the ground and began forming a huge flammable vapor cloud. The vapor cloud expanded in just 90 seconds, engulfing the unit and the nearby trailers full of workers. About 25 feet from the base of the blowdown drum, 2 workers were parked in a pickup truck with the engine idling. As flammable vapor entered the air intake, the diesel engine began to race. The 2 workers fled, unable to shut off the engine. Moments later, witnesses saw the truck backfire and ignite the vapor cloud. Powerful explosions swept through the area. The blast pressure wave accelerated through the ISOM unit, causing heavy destruction and igniting fires. The workers inside the trailers were right in the path of the explosions. The fires continued to burn for hours. 12 of the 20 occupants of the double-wide trailer were killed, along with 3 workers in a trailer nearby. 180 workers were injured, many with serious burns, fractures, or other traumatic injuries. The wood and metal frame trailers were blown apart by the blasts. Firefighters struggled to rescue the injured and recover the victims. 50 large chemical storage tanks were damaged, and the ISOM unit remained shut down for more than 2 years. The disaster at BP Texas City was the most serious refinery accident ever investigated by the CSB. February 8, 2017, the Packaging Corporation of America's DeRidder, Louisiana pulp and paper mill. The mill was undergoing a planned maintenance shutdown when a tank violently exploded, killing 3 contract workers and injuring 7 others. The Chemical Safety Board launched an investigation and found that despite industry good practice guidance to do so, PCA did not apply its process safety management system to the process that included the tank that ultimately exploded. As a result, hazards, such as the potential for a flammable atmosphere to form within the tank, were not adequately evaluated.
Had the company voluntarily applied its safety management system, which is used elsewhere in the mill, to the process that included the tank, the conditions that allowed the fatal explosion could have been eliminated or controlled, and this tragic incident could have been prevented.
PCA's DeRidder mill produces container board that is used in products such as boxes and container board displays. The container board is made from pulp produced at the facility. The process of creating pulp generates vapors. The vapors, which contain water, turpentine, and various sulfur compounds, are then collected and separated. The vapors are separated in a turpentine stripping column. Most of the turpentine is removed and sent to a condenser. The vapors remaining condense to a liquid containing mostly water, but also residual amounts of the sulfur compounds and turpentine. The liquid is known as foul condensate. The foul condensate is sent from the stripping column to an approximately 100,000-gallon capacity tank used to store the liquid at or close to atmospheric pressure. The foul condensate tank is primarily used to regulate the flow of liquid between the turpentine stripping column upstream and a downstream unit that removes the remaining sulfur components from the foul condensate. During the February 8th incident, the mill was undergoing an annual shutdown, during which employees and contract workers performed maintenance, inspection, and upgrade tasks throughout the facility. One task was to repair the water piping located above and connected to the foul condensate tank.
If you can't talk,
the piping had shifted and cracked months earlier. The repair required welding on the piping, commonly referred to as hot work. To prepare for the hot work, valves were closed leading into and out of the foul condensate tank, while 10 feet of liquid remained inside. The foul condensate was left within the tank partially because there were no plans to work directly on the tank during the outage. The company also assumed that the tank contained mostly water, was sealed off from the atmosphere, and did not pose a safety risk. These assumptions, however, were incorrect. Residual turpentine, which is normally present in foul condensate, collected on top of the liquid in the tank due to its density. The foul condensate tank was designed so that by changing the height of the liquid level inside the tank, the residual turpentine would be skimmed off and sent to a turpentine recovery system. But in the months leading up to the incident, the turpentine was not removed because there was confusion as to which department at the mill was responsible for operation of the foul condensate tank. Due to this lack of defined responsibility, the valve designed to direct skimmed turpentine to the mill's turpentine recovery system remained closed during those months. As a result, more flammable turpentine was in the foul condensate tank during the shutdown than anyone expected. In addition, it is normal for there to be vapors inside the foul condensate tank in the space above the liquid. Although those vapors can be flammable, there is not supposed to be enough oxygen in the tank to support combustion. But because the tank had been isolated from the process during the annual shutdown, the contents of the tank likely cooled from its normal operating temperature, creating low pressure conditions within the tank. This most likely triggered a relief valve on the tank's roof to add more air to avoid damaging the tank from a vacuum created by low pressure. The vacuum relief valve was likely one of the few potential sources that allowed enough air into the tank to create an explosive atmosphere. The day before the incident, in preparation for repair, the water piping was isolated from the foul condensate tank and the rest of the process by closed valves, and the piping was separated physically from the tank. Around 8 a.m. on February 8th, a mill employee used a gas detector to check for a flammable atmosphere in and around the water piping, and found none. The company then issued a hot work permit for the welding work. But even though a flammable atmosphere was not present outside the tank, there was a flammable atmosphere inside the tank. Without knowing that the vapors inside the tank posed a serious hazard, 3 contract workers began welding on the water piping located above it. The CSB was unable to determine an exact ignition source, but it is likely that sparks or molten slag produced from the hot work landed on or near the foul condensate tank, heating up the tank wall or igniting its contents. Or it is possible that the hot work was complete, but as the tools were lowered, a welding torch fell and created an electric arc on the tank or its vent piping. Regardless, the CSB determined that hot work activities likely ignited the flammable vapors and liquid turpentine inside the foul condensate tank. At 11:05 a.m., there was a massive explosion. The tank separated from its base and launched up and over a 6-story building, landing approximately 375 feet away. 3 people were killed and 7 were injured. All were contract employees working near the foul condensate tank.
In our investigation, we found that PCA missed opportunities to identify, evaluate, and control the hazards that led to the explosion. That is because a process safety management system was not applied to the process that includes the foul condensate tank.
OSHA's Process Safety Management, or PSM standard, requires facilities that use highly hazardous substances to have a process safety management system in place to protect workers from catastrophic incidents. But this safeguard was not required for most of the process system that included the foul condensate tank, known as the non-condensable gas system. The CSB notes that although not required by federal regulation, industry good practice guidance recommends having a robust safety management system to manage the hazards related to processing non-condensable gases. But despite these recommendations, PCA did not voluntarily apply its process safety management system required by OSHA elsewhere in the mill to the non-condensable gas system. As a result, PCA never conducted a process hazard analysis of the non-condensable gas system. A process hazard analysis, or PHA, is a comprehensive assessment of potential hazards involved in an industrial process. A properly conducted PHA likely would have identified and called for elimination of the flammable atmosphere inside the foul condensate tank during the annual shutdown. On the day of the incident, the 30-foot tall tank contained a liquid level of about 10 feet, and PCA employees thought that the remaining 20 feet of vapor space lacked enough air to support combustion. But a PHA could have recognized the potential for air to enter the tank and create a flammable atmosphere, which could have identified the need for the company to implement effective safeguards to prevent an explosion. For example, the tank could have been drained and purged as part of the annual shutdown. Steve Salmon is Assistant Director of the Health, Safety, and Environment Department of the United Steelworkers, the union which represents PCA employees.
Decisions were made to not drain, flush, and leave the foul condensate tank open, and that is different than what it's been in the past. Our members felt that needed to be done. We believe that had the tank been drained, flushed, and left open, that could have helped prevent this unwanted event.
Other safeguards include procedures to prohibit hot work near the foul condensate tank while it contained flammable vapor, low pressure alarms to alert workers that the vacuum relief valve may open and allow air into the tank, oxygen analyzers that let workers know that a dangerous amount of air was in the tank, interlocks to automatically reduce the concentration of oxygen by adding an inert gas so that a flammable atmosphere does not form, or an inherently safer tank designed to withstand full vacuum conditions, eliminating the need for a vacuum relief valve and the potential risks associated with it. The foul condensate tank was located between two operations areas, the pulp mill and the powerhouse. But because the DeRidder mill did not apply its process safety management system to the foul condensate tank, the company did not clearly identify who was responsible for it, leading to confusion within the mill workforce. Over time, this ambiguity led to few operators knowing much about the tank, its contents, and its explosion potential.
Training and education needed to be provided to the operators and workers in the area. Workers were not aware of the hazards. They were not provided with that information. They felt that this tank would not be an issue.
In its final report, the CSB provided safety guidance to pulp and paper mills that operate non-condensable gas systems, which includes all foul condensate tanks. The guidance includes apply effective process safety management systems to non-condensable gas systems using good practice guidance. Consider expanding the boundaries of process safety management programs beyond the units covered by OSHA's PSM standard. Apply industry standards for explosion prevention and safety interlock systems. And provide workers with periodic training to ensure they understand all process safety hazards applicable to areas of their responsibility, including the safety conditions needed to permit hot work. Also, in its final report, the CSB reiterated a 2002 recommendation to OSHA to revise the PSM standard to cover atmospheric storage tanks that could be involved in a potential catastrophic release as a result of being interconnected to a covered process with 10,000 pounds of a flammable substance.
That recommendation has not yet been implemented, and explosions like the one at PCA continue to occur. We urge OSHA to act on this important safety recommendation to prevent future incidents.
What's unique about pulp and paper mills, it's not just a mill that makes paper. It needs to be viewed as a chemical plant that makes paper and handled in that fashion around process safety management to prevent tragedies from happening.
Preventable incidents like the one at PCA reveal flaws in the facility's process safety management system. We believe our safety guidance and recommendation for stronger OSHA safeguards will help prevent these tragic incidents.
Ma'am, I'm afraid that
Thank you for watching the CSB safety video.
For more information on the CSB's investigation, please visit csb.gov.
Order on my way. I'm listening. On my way to hospital. Standing by. Reporting. On my way. Reporting. 10-4.
April 26, 2018, the Husky Superior Refinery in Superior, Wisconsin. At 5:40 a.m., operators took steps to shut down the refinery's fluid catalytic cracker, or FCC unit, for periodic maintenance and inspection. The FCC unit uses heat and a solid catalyst to break or crack heavy hydrocarbons from crude oil into smaller hydrocarbons, which can then be blended into gasoline and other products. Slide valves control the flow of catalyst between a reactor, which contains flammable hydrocarbons, and a regenerator, which contains air. It is important to prevent mixing the hydrocarbons and air, since if they mix, a dangerous explosion can occur. To avoid this hazard, the slide valves maintain a catalyst level between the reactor and regenerator, which acts as a barrier. To initiate the shutdown of the FCC unit, refinery workers stopped the flow of hydrocarbons to the unit and closed the two slide valves connecting the reactor to the regenerator. But unknown to the workers, one of those slide valves was eroded, and even though it closed, it could not maintain a catalyst barrier in the reactor. As a result, the catalyst from the reactor fell through the valve to the regenerator, leaving no protective barrier between the two pieces of equipment. This allowed air from the regenerator to flow backwards through the slide valve into the reactor, and then into equipment downstream of the reactor, which contained hydrocarbons, forming a flammable mixture. At approximately 10 a.m., the hazardous mixture of air and hydrocarbons found an ignition source, and there was a large explosion. Debris from the explosion flew about 200 feet and hit a large above-ground storage tank, puncturing the side of the tank and releasing hot asphalt. Asphalt poured out of the tank over the containment drum and into the refinery's operating units, where it spread along the ground. At around 12:15 p.m., the released asphalt ignited near the storage tanks, and a fire broke out. The fire traveled along a stream of asphalt to the refinery's crude and FCC units. The fire produced a huge plume of black smoke, leading to the evacuation of a portion of the town of Superior. Typically, this type of asphalt fire can burn for days. A plan to extinguish the fire was developed by the refinery's emergency response team. Around 3 o'clock, they began to address the asphalt fire together with the Superior Fire Department. A fire truck drove to the edge of the crude unit, and emergency responders sprayed dry chemical fire extinguisher inside to fight the fires that had broken out there. Responders also used 2 stationary hoses called monitors to shoot water into the crude unit in an attempt to extinguish the flames. While these fires were being put out, over by the storage tanks, emergency responders began to approach the large area of burning asphalt. The emergency responders' plan was to push the asphalt fire into an empty area near the storage tanks, and then aggressively attack the fire from multiple directions. First, they used 2 monitors, one to the north and another to the west, to sweep water to push the asphalt fire toward the designated containment area. Then, when the fires within the refinery's units had been extinguished, the fire truck relocated so that it could spray the burning asphalt in the containment area with foam from the east. Around 5:30, an additional team began to attack the fire from the south, spraying foam from a monitor. At this point, the asphalt fire was completely surrounded within the containment area. With the fire contained, emergency responders were able to put out the asphalt fire at around 7 p.m. The asphalt fire had been extinguished in a matter of hours, as opposed to days, as had been initially feared. The evacuation order was lifted, and Superior residents were allowed to return home. Nevertheless, 36 Husky employees and contract workers sought medical attention for injuries.
911, what's your emergency?
Hi, there's a strange car parked here. Could you check it?
Where's the car parked?
It's a restricted area.
Can you give me the address of where this car is parked, sir? So what is it about this parked car that has you concerned, sir?
Private cars are not allowed to park here.
Why is that, sir?
It's for safety reasons. Maybe I'm overreacting, but could you send the police to check it?
January 22nd, 2018. The Pryor Trust gas well in
Hello?
Pittsburgh County,
Are you still
Oklahoma.
there?
The well was operated by Red Mountain Operating LLC, which contracted the Patterson
Yes, of course.
UTI
I'll
drilling
send the police
company
to check the
to
car.
drill the well.
Thank you. Bye.
In order to change a drill bit, crew members removed the drill pipe from the well. Approximately 3.5 hours later, a blowout and rig fire occurred, killing 5 workers.
Industry best practices recommend having 2 protective barriers in place at all times during drilling operations. But our investigation into the incident at the Pryor Trust well found that both of those barriers failed. The safety management system utilized at the well was simply not effective, and the result was a catastrophic blowout and fire.
Case resolved. What are the orders heading over there?
The Pryor Trust gas well was comprised of vertical and horizontal sections being drilled to reach underground natural gas in the Woodford Geological Formation. During drilling, a diesel oil-based liquid called mud is pumped down through the drill pipe and back up through the area of the well outside of the drill pipe, called the annulus. When mud returns to the surface, it includes rock cuttings from the bottom of the well. Mud, however, has another important function. It is designed to add pressure to the well so that gas within the exposed geological formation is unable to enter the well during drilling. If that happens,
Is anybody
and the
injured?
gas is not detected, it can lead to a dangerous blowout. On January 21st, 2018,
Did you see if they had
Patterson
any
crew
weapons?
members had been drilling the well for 10 days under the supervision of 2 contracted representatives
of them are
from
there?
Red Mountain. They were drilling the horizontal section of the well.
Can you give me a
That
precise
morning,
address of the
a
incident?
crew member called a mudlogger studied the rocks returning to the surface and found they were different than expected. He believed the drill pipe had inadvertently entered a
Maybe it's
different
possible
geological
it's
formation
Do you think
where
you
Red
could do that,
Mountain
Matt?
did not intend to drill. Shortly after, gas started to escape from mud returning to the surface. The gas caused mud to spit out of equipment near the well and cover a portion of the rig. Around 11 a.m., the drilling crew adjusted piping so that mud returning from the well was routed to a piece of equipment called a mud gas separator that removed the gas from the mud. The separated gas was then routed to a flare to safely burn it. The size of the flare indicated that there was a significant amount of gas in the mud and that the well had likely become underbalanced, meaning that pressure from the mud was not keeping gas out of the well as intended. The crew continued drilling underbalanced until 3:30 p.m. and they stopped because the drill bit had become worn and needed to be replaced. The crew first circulated the well for 3 hours by pumping mud down the drill pipe and up the annulus. The flare continued while the well was circulating, an indication that the well remained underbalanced. While circulating, the Red Mountain representatives discussed how to remove the drill pipe from the well in order to replace the drill bit. The process to remove a drill pipe is called tripping. During any tripping operation, mud is pumped into the well to replace the volume of drill pipe being removed, which prevents gas from flowing into the well. In this case, the Red Mountain representatives decided to use a tripping method called calculated fill, which involved periodically pumping a calculated amount of mud into the well as the drill pipe was removed. They believed this method would keep the well contained if gas entered during the operation. But it was not a standard tripping method during normal drilling, so no one on the Patterson crew had performed it before, and they had no written procedure. The crew started removing the drill pipe at 6:47 p.m. The CSB found that while tripping the drill pipe from the horizontal section of the well, not enough mud was pumped and gas entered the well. The driller, who was controlling the operation from inside a building on the rig called the driller's cabin, did not see the discrepancy. That is because he had not been sufficiently trained on a new electronic version of a trip sheet, which is a form used to monitor and calculate whether a well is taking the proper amount of mud during tripping. As a result, he was unable to see that a significant amount of gas continued to enter or expand within the well, causing pressure in the well to increase and mud to backflow into a tank at the surface called the trip tank. In fact, pressure at the surface of the well had increased so much that the centrifugal pump the crew was using was no longer able to pump mud against the pressure of the well. Red Mountain's representatives decided to switch to higher pressure pumps, called mud pumps, to try to force mud into the well. They believed that the pressure applied by the new pumps would push any gas out of the well. But by the time the drill bit reached the top of the curve in the well, the CSB found that, unknown to drilling crew members, 20 barrels of gas had entered or expanded within the well. At that time, the drilling crew performed a 45-second flow check to see if gas was flowing in the well. The crew did not observe any flow of gas and believed the well to be stable, but the CSB determined that the flow check was inadequate. At 11 p.m., the drilling crew again circulated the well. While circulating, the rig's mud pits, which are tanks used to hold mud at the surface and are equipped with level sensors, gained 14 barrels of mud when they should have remained stable. This meant that the well gained approximately 14 barrels of gas, which caused the mud to escape at the surface. But the night shift driller had turned off the alarm system before the tripping operation, and no alarm sounded, so the large gain went unnoticed. Red Mountain's representatives then decided to pump a weighted volume of mud called a pill into the well, meant to generate enough pressure to prevent gas from entering the well. But a Patterson drilling crew member misheard Red Mountain's instructions over the radio, and they accidentally added lost circulation material to the pill. This material is designed to clog breaches in the well and is not intended to be in weighted pills. Although the mistake was discovered, the pill containing the lost circulation material was pumped down to the bottom of the drill pipe, clogging it. By 1:12 a.m. on January 22nd, the crew started to remove the drill pipe from the vertical section of the well, this time using the typical industry tripping method called continuous fill, where mud is pumped continuously into the well as the drill pipe is removed. But because the drill pipe was clogged, the mud was not freely draining into the well. The crew attempted to pump a weighted slug of mud into the drill pipe to push the clogged mud out, but this was not successful. With the drill pipe plugged, the drilling crew had to trip wet, meaning mud was in the pipe sections being removed at the surface. The drilling crew used what is known as a mud bucket to collect the mud from the drill pipe, which they drained into the trip tank. But the trip tank was also used to pump mud into the well during tripping. So the trip tank volume started to fluctuate as mud was pumped out to the well and drained in from the drill pipe. The fluctuations confused crew members, and they did not realize that while the drill pipe was removed from the vertical section, the well gained another 23 barrels of gas. When the bottom hole assembly, which is equipment at the end of the drill pipe that includes the drill bit, was near the top of the well, the crew finally removed the plugged part of the drill pipe. For the next hour, they tried to clear the clog. But at that time, and during a subsequent shift change, the well was still flowing, gaining another 31 barrels of gas and pushing more mud into the trip tank. No one saw the gain. At 6:10 a.m., the crew lifted the bottom hole assembly out of the well and closed the blind rams on the blowout preventer. They prepared a new bottom hole assembly for testing. When it was ready, a drilling crew member checked a pressure gauge on the rig floor to see if it showed pressure in the well, a safety precaution used before opening the blowout preventer. The pressure gauge showed no pressure. But at 7:57 a.m., when the blind rams were reopened so the new bottom hole assembly could be lowered into the well, 5 barrels of mud surged to the mud pits. At that time, a crew member pulled away the steel plate that had been covering the hole in the rig floor over the well. He waved over another worker who saw mud bubbling in the well, a sign that there was a significant amount of gas in the mud. That worker later told the CSB that he does not know if the mud bubbling was communicated to the driller. Between 7:57 a.m. and 8:35 a.m., while the drilling crew was testing the new bottom hole assembly, the mud pits gained another 102 barrels of mud, a very large volume. This significant gain likely displayed on the driller's data screen. But the day shift driller also chose to turn off the alarm system, and it is unknown if the driller saw this dangerous gain. At 8:35, with testing complete, the bottom hole assembly was removed from the well, and the mud pits gained another 12 barrels of mud, for a total influx of 207 barrels of gas into the well from the start of the tripping operation. A crew member saw mud flowing up out of the open blowout preventer stack. The mud was shooting up steadily, getting closer to the rig floor. The crew member told the driller, and the driller responded, that he was going to close the blind rams, but he never made it. Seconds later, mud blew upwards out of the well in what is known as a blowout. 2 workers on the rig floor ran into the driller's cabin, where 3 other workers were already located. The gas and mud then ignited, causing a massive fire. All 5 people in the driller's cabin were killed. The blowout continued for hours until a well control services company was able to shut in the well around 4 p.m. During its investigation, the CSB found data indicating that on the evening prior to the blowout, the night shift driller turned off the entire alarm system. Data also indicates that the day shift driller briefly turned on the alarm system, but then quickly turned it off again on the day of the incident. Other than that short period, the alarm system was off for 14 hours, leading to the blowout.
We were not able to conclusively determine why the drillers turned the alarm system off. A possible reason why they did is that the alarms were perceived as a nuisance or an annoyance. In fact, we found that had the alarm system been on, most of the alarms that would have activated during the 14 hours leading up to the incident likely would have been irrelevant to detecting the problems in the well.
For an alarm system to be effective, it must be configured so that the driller only receives alerts to conditions that require attention. But the CSB found that Patterson did not develop guidance to help drillers set the alarm system for the various operations performed on the rig, such as drilling, tripping, and circulating. Instead, to manage the alarm rate, both drillers apparently elected to simply turn off the alarm system.
We concluded that what's called a state-based alarm strategy is one way to solve this issue. For example, on a drilling rig, there could be different active alarms for each operation, such as drilling, tripping, and circulating, so that alarms critical to a certain operation do not become a nuisance when operating in a different state where those alarms are not needed.
Although there is a large body of guidance and recommendations on the design of alarm systems for hazardous operations, none are specifically targeted for the drilling industry. As a result, the CSB made a recommendation to the American Petroleum Institute to develop a standard on alarm management, specifically for the drilling industry, that addresses drilling's unique dynamic environment and provides guidance on implementing a state-based alarm system for different operating modes.
When the blowout started, 2 crew members on the rig floor ran inside the driller's cabin. 3 other crew members were already in the driller's cabin, and all 5 workers were killed.
It is unknown how long the victims remained alive inside the driller's cabin, but they had no viable escape routes. There were 2 exit doors from the driller's cabin, but both of those exit doors were blocked by flames after the gas and mud ignited. The CSB concluded that had the fire rating of the driller's cabin been insured for a minimum time, with emergency escape options from the floor or from the back wall, there could have been a better chance for the workers inside to have survived this incident. Stan Christman is a drilling expert who consulted with the CSB on the prior trust investigation.
On a drilling rig, the operations are controlled from the driller's cabin by the key man, the driller. And he has a crew that works for him on the rig floor. The driller's cabin is located right next to the rig floor. He can see, talk over radio, even directly to the crew and get things done. Having the driller's cabin near the rig floor puts it closer to the hazards, and that is things happening on the floor, typically from the well. And these hazards are things that we probably think further about. How do we improve the reliability and safety of these cabins
911.
for these unusual events?
Although there are best practices within the chemical industry for the location and design of control rooms, there is no guidance specific to drilling. As a result, the CSB made a recommendation to the American Petroleum Institute to develop guidance addressing the protection of onshore rig workers from fire and explosion hazards in the event of a blowout. The guidance will specifically address the design and location of the driller's cabin and establish minimum required evacuation methods from various locations on the rig.
Can help us find it. Is it in a car? Is it in a suitcase?
Flow
or a
checks
backpack?
are a safety-critical operation used to determine if gas or other formation
sir, I'm
fluids
notifying
have
officers
entered a
working
well,
at the festival.
which
I have
could
fire and
lead to a
ambulance
blowout.
responding as well. Thank you.
Patterson policies required flow checks to be performed at various times during the tripping
Emergency
operation.
services are on the way.
But the CSB found that of the 27 flow checks that were required by Patterson during the drilling of this well and the previous well, only 2 were performed, and those were inadequate.
There was a culture on this rig that accepted the non-performance of flow checks. Performing flow checks during the tripping operation, as required by Patterson, could have identified that the well was flowing and could have prevented the blowout.
The CSB found that the cause of the blowout and rig fire was the failure of both barriers that should have been in place during the operations leading to the blowout. Those 2 barriers were the primary prevention barrier, hydrostatic pressure produced by drilling mud, and the secondary mitigation barrier, human detection of gas entering the well and activation of the blowout preventer. When the well became underbalanced on January 21st, the primary protective barrier was lost, but work was not stopped so that the barrier could be reestablished by increasing the weight of mud, and no analysis on the loss of the barrier was performed.
We learned that Red Mountain had developed what they called a drilling prognosis, which is a type of well plan. But that plan did not specify what barriers were required or how to identify if a barrier was lost. And we found that development of a more comprehensive plan, such as what's known as the Well Construction Interface Document, which is used more widely in offshore drilling, was not required.
In fact, there are minimal federal regulations governing the safety of onshore oil and gas drilling operations. The Occupational Safety and Health Administration's Process Safety Management, or PSM standard, which would require a hazard analysis of the operation, does not apply to drilling. No other OSHA standard specifically covers drilling, and no other federal regulatory body oversees the safety of onshore drilling operations. With no federal safety standards for oil and gas drilling companies are governed by a patchwork of individual state laws. During its investigation, the CSB determined that the laws in Oklahoma, where the incident occurred, are not focused on safety, and instead stress maximizing production and eliminating the loss of hydrocarbons.
The CSB believes more focused and specialized regulatory coverage, like the OSHA PSM standard for the chemical industry, is needed to better control the hazards inherent to drilling. With the requirement for a more effective safety management system, drilling companies can avoid incidents in a proactive manner, protecting both their workers and the environment.
As a result, the CSB made recommendations to OSHA to either apply the PSM standard to drilling of oil and gas wells or develop a new standard with a safety management system framework similar to PSM that applies only to the drilling of onshore oil and gas wells. To prevent similar blowouts, drilling contractors and operators should develop a well construction interface document, bridging the operators and drilling contractors' safety systems and providing a barrier plan, including how to monitor barriers and how to respond if a barrier is compromised. Create procedures for operations, including tripping. Design alarm systems so that only the alarms indicating a condition needing drilling crew attention are active. Regularly perform drills to test drilling crews' abilities to detect and respond to signs of influx. And implement an indicators program to monitor and improve policy implementation rates.
The blowout and massive fire at the Prior Trust well was completely preventable. We hope our findings and recommendations are used by the drilling industry to promote safer operations so that similar tragic incidents can be prevented. Thank you for watching this CSB safety video.
I'm listening. Heading over there.
What are the orders? Heading over there.
Suspects awaiting transport. Police transport needed.
Sorry, time for thank you. Case resolved.
Suspects in custody requesting transport. Police
Waiting for my way.
What are the orders? Going there. Waiting for orders. Understood. We are ready. Going there.
June 21st, 2019.
We are ready. 10-4.
The Philadelphia Energy Solutions Refinery in Philadelphia, Pennsylvania. At 4 a.m., flammable process fluid containing mostly propane, along with a small concentration of highly toxic hydrofluoric acid, or HF, escaped from the refinery's HF alkylation unit, likely through a ruptured pipe elbow. The alkylation unit produced components of high-octane gasoline. The leaking process fluid formed a large ground-hugging vapor cloud that surrounded some sections of the unit. 2 minutes later, the cloud ignited, causing a massive fire. The control room operator quickly took steps to prevent the release of additional HF by rapidly draining the unit's hydrofluoric acid to a special vessel designed to hold the acid in the event of an incident.